Okay. So it says many decisions can be made by assigning probabilities to all possible outcomes pertaining to a situation and then evaluating the results. For example, I can assign probabilities to the number of students who will get an A, B, C, D, and F in the course. This is called a probability distribution, and the formal definition is this. A probability distribution is a table, graph, or formula that lists all the values of a random variable I just need to put the word random in there. And the corresponding probabilities.
Recording in progress.
So there's two different types of probability distributions we'll look at. In this chapter, we look at discrete, so whenever there's a countable number of outcomes. And the next one, we look at continuous, where there is an infinite number of outcomes within an interval of values. So there are different probability distributions depending on the type of variable. So before moving on, let's review the difference between discrete and continuous. So remember, discrete was where we could count the number of outcomes or count the variable we were looking at. Continuous is where it would take on any value in an interval. So we made the distinction between looking at a couple of examples in these in another chapter previously. And in this chapter, we're just going to look at the first. We're just going to look at what's a discrete probability distribution. So where we can list the possible outcomes, we can actually count them, and we can list their corresponding probabilities. So recall that from chapter 1, a variable is a characteristic or attribute that can assume different values. Since the variables in this chapter are associated with probability, and remember back to probability, we talked about that probability is looks at random chances and the chance of that happening, or the chance of random circumstances, we'll say that. These are called random variables that we're looking at because probability is random. So basically, a random variable is a variable whose values are determined by chance. And a discrete probability distribution lists all the possible outcomes and the corresponding probabilities. So if we go down here, a discrete probability distribution consists of the values a discrete random variable can assume and the corresponding probabilities of the values. So let's look at an example. So this says fair dice rolled. Here's the probability distribution. So what it looks at is first in the top, we have the outcome. So this is the possible numbers you could get from the die roll. So up here in the top, you have the numbers 1, 2, 3, 4, 5, and 6. And then in the bottom, it shows what is the probability for each of these. And we know that back to chapter 4, for each of these, the probability it happens is just 1/6, right? So the probability down here is a 6 for this one, 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 and a 6 for this one. And whenever you join, make sure your mic's off too, or else it'll kind of echo on my end. All right. So formally, for a probability distribution to be valid, it must satisfy two conditions. So we talked about these in the last chapter, that the probabilities for each of the outcomes must be between 0 and 1, including 0 and 1. So what does that mean? That P of x, the probability of any particular outcome in the sample space, is between 0 and 1. And it can include 0 and 1, right? If something is obviously impossible to occur, it has probability of 0. And if it's definite to occur, it has probability 1. And the other one is the sum of the probabilities actually equals 1. We talked about this in chapter 4, right? What did I say? Whenever we add up all the probabilities associated with each of these outcomes, we indeed do get 1. So let's check if this one down here is a probability distribution by checking these two conditions. So let's ask ourselves first, one, is all these probabilities in the bottom row between 0 and 1? So 0.2, yes, it's in there. 0.6 is in there. 0.1 is in there. 0.3 is in there. And 0.05 is in there. So yes, in this case, all the probabilities are between 0 and 1, including 0 and 1. So now, let's look at the second condition. Do they sum to 1? So, is the sum of the probabilities equal to 1? So all I do is sum all of them. So the sum of the probabilities is 0.2 plus 0.6 plus 0.1 plus 0.3 plus 0.05. Someone tell me what you get when you sum all of those numbers together. You can type in the chat. Yeah, 1.25 is correct. So when I sum all of these probabilities that it gives here, I get 1.25. And obviously that is not equal to 1. So this implies that no, the sum, the probabilities does not equal 1. Thus, it is not a probability distribution. So that one wasn't too bad. We just have to check those two conditions and be able to do something like this on the test. So be able to determine if something is a probability distribution by looking at the probabilities for each of the outcomes and seeing if it satisfies these two conditions. And also, if I give you, say, for instance, one of these values is gone from this probability distribution, say I didn't have this here, and I said it's some constant C. what I want you to be able to do is figure out what is the value of C right here that makes us a probability distribution. And we'll talk about how to do that later. So moving on for now, we've been able to check if something is a probability distribution or not. Let's look at one that's a little bit more complicated. So if we were in class right now, I'd actually list out the sample space by drawing it out on the board. But obviously we're not in the classroom right now. So we'll just list it out by hand. So it says 3 fair coins are tossed consecutively. Create a probability distribution for the number of heads. So first I want to look at what's the sample space. So the sample space S, I'm just going to list it out, consists of the following outcomes. So the first one is a head, head, head. Then we have a head, head, tail. Then we have a hail, ted, hail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. And there should be 8 outcomes here if I count them all. 1, 2, 3, 4, 5, 6, 7, 8. So remember, I kind of tried to hint at this a while back, but if you have a thing that you're doing that only has 2 possibilities, so tossing a coin, doing true and false questions, then the number of outcomes in the sample space S is going to be 2 to the n power. So n is just however many times you're doing this. So say, for instance, here we tossed the coin 3 times, so n is 3. So the number of outcomes in S is 8. If we would have done this just twice, then remember, the number of outcomes would be 4, just 2 to the second. So now that we've defined what the sample space is by listing it out, now we want to see what values can X assume. So remember here, X is the number of heads. So a random variable, capital X, represents the number of heads. So we need to look up here on our sample space S and see what's the smallest number of heads you can get. What's the largest number of heads you can get? So the smallest number of heads that you can get occurs here when you have tail, tail, tail. And how many heads do you have in that case? Anyone have any guesses? How many heads are there when you have a tail, tail, tail? It's a trick question. There's 0, right? So the lowest we're going to have is 0. And then whenever I have head, 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 how many heads are there? Obviously, that one there is what? 3, right? So then the values that X can assume, so X consists of the set 0, 1, 2, and 3. And if you go back up here, you can see that there's places where there is just 1 head, and there's just 2 heads, and there's 3 as well. So now what we want to do is create the probability distribution for this. So what I'm going to do is first list out the numbers that the probability or the number of heads in the top. So the number of heads here and this is X, right? This is our random variable X. And down here on the bottom, we have the probabilities for each of these. So here is P of X in the bottom. So, and we just said that we can have x being 0, 1, 2, and 3. So now we want to look at what's the probability of each of these. So how many places do we have 0 heads? And there was only how many? So 0 heads is whenever we have that tail, 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 right? Right here. So the probability of that happening of 0 heads is there's only one time it happens out of 8 possibilities. So its probability is an 8. Right? So we just had one way we could have 0 heads out of 8 possible ways. Now, let's look at whenever we have one head. So one head can occur. Let's look. Here's one of them. Here's one head. Here's another. And there should be one more right here. So there's 3 possible ways that can happen, right? So there's 3 possible ways we can get just one head out of 8 possible outcomes in the sample space. So the probability of 1 is 3/8. And then moving on to whenever we have 2 heads. So that could happen when we are right here, and right here. So again, there's 3 possible ways that could happen out of 8 possible outcomes. So this probability of x being 2, or the probability of getting 2 heads, is also 3/8. And then finally, what's the probability of getting 3 heads? It's what? There's only one way it can happen right here. When you get head, 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 there's one of those out of 8 possible outcomes in the sample space. So the probability of x being 3 is 1/8. So that one wasn't too bad because the sample space was quite small. So you were able to identify where these could happen. And then if you're given a probability distribution like this, if you're able to calculate the probability for each of these by just looking at how many times it occurs, then you can also graph this, and it would look something like this. On the y-axis goes the probabilities. On the x-axis goes the number of heads. So all we're looking at is on this x-axis here goes the possible outcomes of x, so 0, 1, 2, 3, and 4. And the y-axis goes the probability. So here, let's say we have, here's 0, 1, 2, and 3. And then on the y-axis over here, we have the probabilities. So let's say here is 1/8, 2/8, and then 3/8 up here. And then all we do is draw a line for each of these to the probability. So here, the probability of x is 0 is 1/8. So I just have a line up to 1/8, right? Right here. Then the next, the probability that x is 1 is 3/8. So I have a line up to 3/8. For when x is 2, the probability is again 3/8. So a line again up to 3/8. And then finally, the probability that x is 3 is 1/8. So a line up to 1/8. So that's one way we could visualize a probability distribution also. Because remember, a probability distribution can be a table, a graph, or a formula. In this case, it's just a graph of it. And this part here that we just did was the table. So that's one example. Let's look at another example. So this is example 2. It says, when given a survey, students were asked how many hours they studied last night. Let the random variable x be the number of hours studied last night. Given the following probability or the following frequency distribution, create the probability distribution for x. So the first thing we want to do is kind of like what we did here when we calculated the conditional probabilities back when we look at contingency tables. We first want to find what's the total. So in this case, if we take all of these number of students in the right-hand column, if I add all those up, what's the total end up being? 27 is correct. So I know the total frequency is 27. And now how do we find the probability for each of these? If we know the number of people that fit into each of these categories and we know the total number of people, then we can calculate the relative frequency. So remember that probability is just a relative frequency. So if I want to know what's the probability that I had a student sleep 0 hours last night, I'm just going to look at the number of people that slept 0 hours and divide by the total number of people. So up here, whenever we're looking at the probability distribution and creating it, so here in the top row is the number of hours studied. And then the bottom is the probability. So let's start off by listing these. So we have 0, 1, 2, 3, and 4. So here we have 0, 1, 2, 3, and then 4. And we just want to list what's the probability for each of these. So what's the probability that a student slept 0 hours last night? So it's the number of people that slept 0 hours, which was 6, divided by the total number of people of 27. What's the probability that x is 1? Yeah, 12 over 27, right? What's the probability that x is 2? 4 over 27, yes. What's the probability that x is 3? Yes, and what's the probability that x is 4? 3 over 27, yes. So all of these, we just use the relative frequency to find the probabilities. And that was quite easy. That's kind of how we did it when we were looking at contingency tables. We would look at how many people fit in a certain category, divide by the total number of people, and it would be a relative frequency. The same thing works here. So far, we've looked at here, we looked at a table and created the probability distribution from that. Here, we looked at given a probability distribution, you can visualize it with the graph. In this case, the next example in here looks at a formula. So here it says, recall that probability distributions can be represented in a formula. Let's say that x can take on values 2, 3, and 6, and we have that the probability is defined as just 1 over x. So verify that this is a proper probability distribution. So we're first going to list off what's the possible outcomes we have. So x up here in the top can take on values. It says 2, 3, and 6. And now the probability for each of these, remember the probability of x is defined by 1 over that value. So whenever I'm looking at x is 2, the probability of that happening is what? Anyone got an idea? Yeah, half, right? Just 1 over 2. What about the probability when x is 3? What's its probability? Not 3 halves, but remember, it's just 1 over the number. So in this case, it's just 1/3. And then finally, what's the probability of x equaling 6? It's what? A sixth, right? So now we've created the probability distribution. Now we want to verify that it is actually a proper probability distribution. So the first question, remember, is do all the probabilities fall between 0 and 1? So are all of these numbers up here between 0 and 1? At least the probabilities, not the numbers in the top, but just the probabilities. Are all of those between 0 and 1? Someone say yes or no. Yes, they are, right? So it satisfies the first condition. Now, the second one. Does the sum of the probabilities equal 1? So I'm going to sum up these probabilities. This is a half plus a third plus a sixth. So it doesn't look like it because there's different denominators, but if you find a common denominator and add, let's see what happens. So 1/2 as a fraction over 6 is 3/6. Then a third as a fraction is 2/6. And then we have 1/6 here. And if I add these probabilities together, 3/6 plus 2/6 plus 1/6 is 6/6 or 1. So yes, the sum of the probabilities does indeed equal 1. So yes, we do have a proper probability distribution. So all we had to do there was check that those two conditions were satisfied for this distribution of probabilities here. The dogs are actually outside by the pool right now. There's like 3 of them. I'm teaching at my girlfriend's grandma's in her dining room. She's sleeping right now. She would not be happy if I woke her up. She didn't like when my alarm went off well, here we're 2 hours behind, so it went off at 9 o'clock instead of 11. She'll come to class one time probably. She comes back with me next month, so I'm sure she'll probably come to our class. All right, so now let's move on to the next section. So in this section, we talk about how to find the mean, the variance, and the standard deviation given a discrete probability distribution. So instead, in chapter 3, we learn how to calculate the mean, variance, and standard deviation for a data set. We can do the same thing with the probability distribution. However, our methods change. So the way we calculate these is a little different. So for instance, when I want to find the mean of the discrete probability distribution, so the mean, we're going to say, is denoted by the expected value. So the expected value of x. And if we write it as a symbol, remember, the symbol for the population mean was mu. And if I want to actually find this, there's a formula we use. So what I do is say x1, so the first outcome, times the probability that that outcome happens, plus x2 times the probability of x2, And then I do this every time until I get to the final outcome, xn times the probability of xn. So if I write this shorthand with a sum, what it looks like is this. The expected value of x is equal to the sum from I equals 1 to n of xi times the probability of each xi. So xi here are just the values of the random variables. In this case, it would be like 2, 3, and 6. Each of those are xi. And the probability of xi are each of these probabilities here corresponding with each of the outcomes. So it'll make a lot more sense when we look at an example here in a second. But let's just look at the formulas, just to kind of wrap our head around it. So the next one is the variance. So this is where it gets a little more complicated. So the variance of x, which if we remember back to chapter 3, the symbol for this is sigma squared. So this one is found a little bit differently. So this is found by the expected value of x squared minus the expected value of x, this quantity squared. So if you notice, there's a slight difference between the expected value of x that we can calculate up here whenever we're calculating the mean and whenever we're calculating this down here. So the difference you'll see in a second when I write out the formula, what the difference between the two is. Okay, so let's fix this real quick. So if I want to write out this part here, the expected value of x squared, it's actually equal to this. So it's the sum from I equals 1 to n xi squared times the probability of xi. So does anyone notice the difference between this here and this here? What is the difference? It's a slight difference, but it's what? Yeah, the squared, right? Here, in this calculation here at the bottom, we have xi squared. And here we just have xi to the 1, to the first power. So let's go ahead and finish this up. So here, the expected value of x squared is found similarly to the expected value of x. All it does is it squares each of the outcomes first. And then we have to subtract off the expected value of x. That quantity squared. And that's how you find the variance. And then to find the standard deviation, remember, what do I do to the variance? The standard deviation is the what? Yeah, it's the square root of the variance. So if I want the standard deviation of x, if we write it out as a symbol, remember it's sigma. All it is the square root of sigma squared, or if you want to write out that formula, it's the square root of the expected value of x, this quantity squared, minus the expected value of x, the whole quantity squared. It's the square root of this. So then, if we want to use these formulas here, let's do this with an example that looks at the previous one that we looked at here, where we looked at the number of hours studied. What we're going to do is calculate what's the mean number of hours studied for the sample, what's the variance, and what's the standard deviation. So here we actually are given the probability distribution again. So first thing we want to do is find the mean. So I'm going to go step by step. So first we're going to find the mean. So remember the mean, if we want to write it out, the expected value of x is equal to the sum of the x's times their probabilities, right? And I want to add all of those up. So what it looks like is this. I want to pair up each of these together, and I want to multiply these. And then I want to add them. So what it will look like is this. I would take 0 times 6 over 27 plus 1 times 12 over 27 plus 2 times 4 over 27 plus 3 times 2 over 27 and then plus 4 times 3 over 27. Someone tell me what that ends up being as a fraction. What does that sum to? Someone put their answer in the chat and we'll see if it's correct. $38 over 27 is correct. So Mason got 38 over 27, and that is correct. So, and if I do this to 3 decimal places, I'm just going to do it for convenience here. If we round this to 3 decimal places, this is 1.407. So that means the mean number of hours studied last night for this sample was 1.4 hours, roughly. So that's how you find the mean. The next step, we want to find the variance. So the variance of x is found by the expected value of x squared minus the expected value of x, this quantity squared. So we actually already have one of these numbers. We just calculated the expected value of x. So we have this number that goes inside here that we're going to square later on. All we need to find is the expected value of x squared. So let's do that. The expected value of x squared is just equal to the sum of the x squareds times their probabilities. So what that would look like is this. We have 0 squared times 6 over 27 plus 1 squared times 12 over 27 plus 2 squared times 4 over 27 plus 3 squared times 2 over 27. And then plus 4 squared times 3 over 27. Now, someone tell me what you get when you sum all of that up. Yes, 3.481 is correct. So this ends up being 94 over 27, or 3.481. But we're not done yet there. That is just the expected value of x squared. Remember, the variance is the expected value of x minus, or the expected value of x squared minus the expected value of x, that quantity squared. So we're not done yet. So this implies the variance of x, remember, is the expected value of x squared minus the expected value of x, this quantity squared. So we know what the expected value of x squared was, 3.481. And the expected value of x squared is just 1.407 squared. So when I take that difference, what do I get? $1.501 is correct. So then if I want to find the standard deviation for this one, it's just the square root of the variance, right? So it's the square root of the variance of x. So it would just be the square root of 1.501 in that case. What is that to 3 decimal places? 1.225 is correct. So that's how we found the mean, the variance, and the standard deviation for that example. We looked at the number of hours studied last night for a random sample of students. So notice whenever I was calculating this mean up here, I referred to it as E of x, the expected value of x. So the expected value of a discrete random variable of a probability distribution is the theoretical average. So basically, the expected value is the mean of the probability distribution. That is why whenever I was writing these formulas up here, notice that I was using this E of x almost everywhere. The only thing that changed is sometimes I put an x squared in there. Sometimes I would just put x, right? And that whatever the power of x was inside this expected value here is the power that we use. So here, whenever we had the expected value of x to the first, it was x to the first times the probability of x. Then when we moved here, the expected value of x squared to the power was 2. Here, the power was 2. So if you want to look at something like this, the expected value of x to the r power is just the sum of x to the r power times the probability of x for each of those. That's another type of rule that comes about from this. So what I'm going to do is we're going to set up the probability distribution for this example here, and I want you to calculate the expected value and write it in terms of the problem here. So let's look at what this one says. It says 1,000 tickets are sold at $1 each for a television valued at $350. What is the expected value of the gain if you purchase one ticket? So you first want to create the probability distribution for x. So we first want to let x be the money gained from buying one ticket. So we need to figure out what are the possible values of x. So let's just think of it this way. Here is x, here's the probability for each of them. So either we could win the TV or we could not, right? So if we don't win the TV, that means we lost $1. We just lost $1. So the first value of x is -1. And what's the probability that that happens? So there's 1,000 tickets being sold and there's only one winner. So there's how many losers? How many losing tickets? 999, right? So the probability that I lose is 999 divided by 1,000, right? Now, what's the other possible value of x? So you may think it's 350, but it's actually what? Anyone got an idea of what the other possible value of x is? So if you win the TV that's valued at $350, but you spent $1 on the ticket, then you've gained 349, yes. And the probability that this happens is what? What's the probability that you gain $349? 1 out of 1,000 is correct. So now what I want you to do for next time when I come to class on Wednesday is I want you to find the expected value and write it in terms of the problem. So all you're going to have to do is use the formula that we just used on the previous page. This one right here for the mean or the expected value of x. All you have to do is use that formula. And it makes it even easier because there's only two possible values for x. So you find the expected value and then you write what does that actually mean in terms of the question. So if I go back to this question here, where we looked at the number of hours studied, so we would just say the mean number of hours studied was 1.407 hours last night. So I want you to interpret that whenever you get to here. The mean number of money you lose or gain when you buy one ticket is whatever you get for the expected value. And we'll pick up there on Wednesday. Are there any questions? I don't know if we'll have class Wednesday or not, to be honest. I don't know how the weather is looking. I've heard it's supposed to snow again. But I'll keep y'all updated. I'll send out an email in Canvas as well. All right. Y'all have a good day.